Hello, we are looking at the third dot point of circular motion, that is the second section of Module 5, Advanced Mechanics. And for this dot point, we just need to use these four equations, right? It's asking us to use the following relationships in order to solve problems, model, and make quantitative predictions about uniform circular motion. So we don't need to derive these four formulas, which is useful. However, some of them are not too difficult to understand. So I will go through a little bit of that. But understanding why these variables on the right will affect the variable on the left can be useful and important for realizing when to use which equation. The main thing is if you see any example of circular motion, you know to look for these four equations, which are all part of your formula sheet. Okay, so first of all, what is circular motion? We said it in previous videos. It's when you've got a mass of some kind. Let's just say we've got a mass, a 1 kilogram mass. Let's make it 1.5 kilograms for the sake of variety. You've got a mass and it's moving around in a circle. Nice big circle. There we go. When it's moving, it has an instantaneous velocity which is tangential to the curve of the circle it's moving in. Let's say its velocity is 2 meters per second in this case. And another very important number is going to be the radius. Now the radius is going to be from the center of the mass to the center of the circle. In this case, let's say that's 3 meters here. So you may have done the experiment that I mentioned in the last video where you have a 3 meter long string that's quite long with a mass attached to the end, and you spin it around at a certain speed and you time it, and you use this equation here in order to see if you're using this equation to see if mv squared over r is actually equal to the centripetal force. And hopefully you get something with a close value. All right, so where to begin? Let's begin with that equation, all right? How to work out the force on this mass? Well, it's mv squared over r. The faster you spin the mass around, the more force it will pull, the more force the mass will be pulling away, the more force you need to keep it in a circle, the faster it's going. However, if you've got a really long radius, you do not need as much force in order to keep it in a circle. If you imagine yourself swinging a ball on a string, right? Really long string, you can be nice and relaxed. You're making really slow sweeping circles, not too much force required on your hand to pull it in. If you've got a shorter string and you've got the same velocity of ball, you have to swing it really, really fast, and your hand's going to have to be holding onto that string pretty tightly. Otherwise, it's going to slip out of your hand. Also, the heavier the mass is and you're still spinning it really fast, that mass, if it's too heavy, is going to slip out of your hand because there's too much force as well. So let's calculate it for this. It's going to be mass, which is 1.5 kilograms, times velocity squared, which is going to be 2 meters per second squared, which is 4, divided by the radius, which is 3. So let's do this. I actually think the numbers worked out pretty simple. 1.5 centripetal force is equal to mass 1.5 times velocity squared. Velocity is 2 meters per second squared, divided by radius, which is 3. 2 squared is 4. 4 times 1.5 is 6. 6 divided by 3 is 2 newtons. In this case, easy. And where is that force? That force is acting on the ball, pulling it down towards the center, keeping it moving in a circle. Now, because the mass is moving in a circle, it is accelerating. Let's look at this top equation here, right? We said last video that an object that's changing direction is accelerating, even though for uniform circular motion, it is not changing in its speed. Okay, still acceleration if it's changing direction, because acceleration is change in velocity. Now, this equation can be derived with a lot of fancy triangle maths and some yeah, similar triangles and things like that. We're not going to do that because this, as I said before, it's just asking us to use the relationship. So how to find the acceleration of the mass? It's going to be its velocity squared divided by the radius. And this makes sense. If it's got a really high velocity, it's going to swap from moving to the left to moving to the right really quickly. So that's a big change in velocity. That's a big acceleration. But if the radius is very large, then even if the ball's moving quite fast, with a huge radius, it's going to take it a long time before it swaps to the other direction. So the acceleration is not going to be as large. For example, me sitting on the Earth is spinning, but it's got such a high radius, such a large radius that it takes me half a day before my direction flips the other way around. Half a day is a lot of seconds. That is not a high acceleration. Um, Even though the speed is really high, it's a big change in speed, but it takes so long for it to happen. Okay, so let's calculate it for this. Let's see what the acceleration is. V squared, so it's going to be 2 meters per second squared, 4 over r. So it's going to be 4 over 3. 4/3, and acceleration, as usual, is going to be meters per second per second. So AC, let's do it in red to be consistent. AC equals V squared, so that is 2 squared over R. R in this case is 3. And I don't have my calculator on me, so I'm just going to leave it as 4/3 meters per second. And you've got to get that extra per second in there for acceleration. Okay. Let's look at this next one. Now, this next one I really like because it looks like a lot's going on at first, but then the more you look at it, the easier it is. This is just a simple distance, speed, time equation. Velocity is equal to displacement over time. In this case, the displacement is 2 pi r. 2 pi r equals the circumference of a circle, and t is the period. In this case, t is the um, time it takes for the ball to spin around. So really you've just got the top 2 pi r is a distance, is a displacement, the circumference, how far the ball is traveling, and underneath the period is the amount of time it takes for one rotation. So it's how far it travels in one rotation divided by how long it takes to do one rotation. Distance divided by time gives you a speed, or in this case, gives you a velocity. So the velocity is 2 meters per second. We don't have the time actually, so we could rearrange and try and calculate time. To rearrange this, you'd have to times both sides by period, so that period comes onto this side over here. So that would cancel, period will come up here, and then you divide both sides by velocity. So velocity would cancel from there and come underneath here. So you'd have period is equal to 2 pi r over v. Period is equal to 2 pi r over v. Um, Sorry, I should have written what those actual values are. 2 pi 3, which is r, 3, over velocity, which is 2. And let me calculate that, and let me calculate acceleration while I'm at it. And bing, magically 9.4 seconds is what 2 pi 3 over 2 gives us. Okay, period, capital T is in seconds, just like lowercase t, time is also in seconds. So we could calculate that. Also, I realize this isn't too hard to actually calculate. 4/3 is just 1 1/3, which is 1, which is 1 1/3. So 1.3 meters per second per second. Okay, we are left with one last equation to look at, and it's the weirdest one of the lot. We'll do it in blue. It's this one here. It's got this strange looking W, and that is angular velocity. Basically, how fast something is moving in a circle, or how fast it's completing the circle. So it doesn't matter if it's got a long radius or a short radius. The amount of the rate at which it completes the circle is what this angular velocity is giving us. Um, and so it is just the change in the angle over time. So if it starts at this angle of 0 and it travels to this spot here, and that is an angle of, um, you know what, I can do an easier example. Let's go for a 90-degree angle, right? Right? So if it travels from here down to here, now it's at a 90-degree angle. The angular velocity would be 90 degrees divided by the amount of time it took to get there. And because I know that it takes 9.4 seconds to do the whole circle, it's going to be a quarter of 9.4, which is going to be half of 9's 4.5. Half of that's going to be 2.25, 2.35. So 2.35 seconds to do a quarter of this, 90 degrees. So the angular momentum is going to be 90 divided by 2.35, which hopefully I've still got my calculator ready here. 90 divided by 2.35. It's going to be 38.3. 38.3 degrees per second. If you measure the angle in radians instead of degrees, you'll get radians per second rather than degrees per second. Now, it's kind of funny that this formula is in the syllabus. As far as I can see, it has no connection to other parts of the syllabus. So unless I can find that connection, I'm not going to focus on it too much. But suffice to say that you are able to use it for problems of uniform circular motion. And that's it. I guess now all you need to do is practice this for other examples.